Hello, I'm Nalin and I'm going to do a demonstration of the project I've done so far for CSCE 5050. Alright, so in the first step, we set up a basic RESTful API communication between a client and a server. On the server side, we use Flask to create simple endpoint called weather, which returns a static JSON response. The server is running locally on port 5026, as you can see on the screen, and on the client side, we use okay. Now on the client side, we use Python's request module to send a HTTP GET request to this endpoint and print the response. So right now this is just a standard HTTP communication. There are no security mechanisms in place yet. Now if we look at this Wireshark capture here, we can clearly see both the request and the response in plain text. JSON data including location and temperature is fully visible. That demonstrates the main limitation of basic HTTP. There is no confidentiality or authentication. Anyone who intercepts the traffic can read the data directly. There is no way to verify if the data has been modified. So this step establishes a baseline system which we will progressively secure in the next phases. Now in task 2, we progressively enhance the security of our system using symmetric cryptographic techniques. We do this in multiple stages to clearly demonstrate confidentiality, integrity, and real world attack scenarios. First, we implement encryption to achieve confidentiality. We use AES in GCM mode along with a shared symmetric key. The server encrypts the JSON data and sends three components to the client: a nonce, the ciphertext, and an authentication tag. The client then uses the same key and nonce to decrypt and verify the data. If we look at the Wireshark capture here, we can see that there is no readable JSON anymore. Instead, we only see the nonce, ciphertext, and tag. This confirms that confidentiality is achieved. Since an attacker cannot interpret the encrypted payload, the nonce is randomly generated for each request, which helps prevent certain attacks such as replay attempts. Next, we isolate integrity by removing encryption and introducing a message authentication code using HMAC with SHA-256. In this case, the server sends plaintext data along with a MAC tag computed using a shared secret key. The client recomputes the tag and verifies it. In Wireshark, we now see that the full JSON data is visible again, along with the HMAC tag. This shows that confidentiality is not provided, but integrity is ensured. Even though an attacker can read the data, they cannot modify it without being detected. To demonstrate this, we simulate a fake server attack. The attacker modifies the data, for example, changing the humidity value, but reuses a previously intercepted MAC tag. Since the attacker does not know the secret key, they cannot generate a valid tag for the modified data. The client detects this mismatch and rejects the response. Okay. To demonstrate this, we simulate it. Now, in this simulation, this confirms that HMAC successfully protects against tampering. Finally, we combine confidentiality and integrity using authenticated encryption code with AES GCM. This allows us to encrypt the data and generate an authentication tag in a single operation. Wireshark again show. Now we can see that the Wireshark again shows only the encrypted data, confirming both confidentiality and integrity. However, even with authenticated encryption, the system is still vulnerable to replay attacks. We demonstrate this by capturing a valid encrypted response and replaying it using a malicious server. Now, now this shows that even with the authenticated encryption, the system is still vulnerable to replay attacks. We demonstrate this by capturing a valid encrypted response and replaying it using a malicious server. Since the data is still valid and correctly authenticated, the client initially accepts it. This highlights that the system lacks freshness guarantees. To address this, we introduce a timestamp into the encrypted payload. The client checks whether the timestamp falls within an acceptable time window. If the message is too old, it is rejected. With this countermeasure in place, the replayed messages are successfully detected and blocked. Overall, this step demonstrates how confidentiality, integrity, and freshness must all be considered together when redesigning a secure communication. Alright, now in task 3, we improve the security of our system by removing the hard coded symmetric key and replacing it with a secure key exchange mechanism. In the previous step, both the client and the server were using a shared key that was manually defined in the code, which is not secure in real world systems. To fix this, we use RSA public key cryptography to dynamically establish a session key. First, the server generates an RSA key pair using a separate key generation script. The public key is shared with the client through an endpoint, while the private key is kept securely on the server. The client then generates a random session key which will be used for symmetric encryption. Instead of sending this key directly, the client encrypts it using the server's public key and sends it to the server. The server then decrypts the session key using its private key. Once both the sides have the same session key, all further communication uses AES GCM for secure data transmission. If we observe the Wireshark capture here, If we observe the Wireshark capture here, we can see that both the session key and the payload are encrypted. There are There are no plain text keys or data visible on the network. This ensures strong confidentiality and prevents attackers from intercepting sensitive information. This approach closely mirrors how modern secure communication protocols like TLS establish secure sessions, where public key cryptography is used only for key exchange and symmetric encryption is used for efficient data transfer. Overall, this step eliminates the need for hard coded keys and significantly improves the security of the system. Okay, now in task 4, we address a critical security problem that still exists after task 3. In the previous step, the client receives the server's public key and uses it to encrypt the session key. However, there is no guarantee that this public key actually belongs to the legitimate server. An attacker could intercept the communication and provide a fake public key. This is known as the man in the middle attack. To solve this problem, we introduce public key certificates similar to what is used in HTTPS and TLS. We create a certificate authority or CA which generates its own RSA key pair. The CA then signs the server's public key using its private key, creating a digital certificate. This certificate includes the server's public key and an identity field, and the signature is encoded in base 64 and structured in JSON format for reliable transmission. On the client side, the CA's public key is preloaded as a trusted root. When the client receives the server certificate, it verifies the signature using this trusted CA public key. Only if the verification succeeds does the client trust the server's public key and proceed with the RSA based key exchange. From our observations, we see that the client explicitly pretends that the certificate is verified before continuing communication. From our observations, we see that the client explicitly prints that the certificate is verified before continuing communication. If the certificate is invalid or tampered with, the verification fails and the connection is terminated. This ensures that the client is communicating with a legitimate server and not an attacker. Once verification is successful, the system proceeds with secure communication using RSA for key exchange and AES GCM for encrypted data transfer. Wireshark analysis confirms that all sensitive data remains encrypted and no plain text keys or messages are exposed. Finally, to conclude, this project demonstrates a layered approach to secure communication. We started with basic HTTP, which provided no security, and progressively added encryption, integrity checks, authenticated encryption, and protection against AAA attacks. We then introduced RSA based key exchange to securely establish session keys and finally implemented certificates to ensure trust and prevent man in the middle attacks. Overall, the system now achieves confidentiality, integrity, and authentication, closely mirroring real world secure protocols. This project highlights how multiple cryptographic techniques must be combined to build a robust and secure communication system. Thank you.